Next, we discuss some application of the mean value theorem. The first application is to detect constant function. Here is the theorem. Suppose that f is continuous on the closed interval from A to B, and f is differentiable on the open interval from A to B, and that f prime of x equal to 0 for every x inside the interval, then f is constant on the whole interval. And an immediate corollary that suppose that we have function f and g are continuous on the closed interval from A to B, and differentiable on the open interval from A to B, and f prime x equals g prime x for all x inside the interval, then there is a constant c such that f of x equal to g of x plus c. In other words, the difference between these two functions is essentially a constant. The proof goes as follows. Consider the function h of x, which equals the difference between these two functions. That is, h of x is equal to f of x minus g of x. Then the derivative of this function h of x equal to f prime of x minus g prime of x. Because of the assumption in this statement, the difference in derivative of these two functions is always equal to 0. So, using the theorem above, we conclude that h of x here must be a constant, and that is the end of the proof. Another application of the mean value theorem is to detect monotone function. So here, let f be a function from some interval I to a set of all real numbers be differentiable on the interval. Then f is increasing even only if its derivative is greater than or equal to 0. It is decreasing even only if its derivative is always smaller than or equal to 0. We can also make analogous statements for strictly increasing, which means removing the equality possibility, and strictly increasing is equivalent to the derivative is strictly bigger than 0. Similarly, strictly decreasing is equivalent to the derivative strictly smaller than 0. Another very important application of the mean value theorem is to detect local extrema. So the theorem here is called the first derivative test for extrema. Let f be a function from some interval a, b to a set of all real numbers. Furthermore, we assume that the function is continuous. Assume that f is differentiable at the open intervals AC and CB. Then if there is a neighborhood C minus delta to C plus delta within this interval from A to B, such that f prime of x is greater than equal to 0 for x between C minus delta to C. So that corresponds to this part of the neighborhood. In this part, we have f prime is greater than 0, greater than equal to 0. So the function f is increasing over this interval. For the other part of the neighborhood, for C smaller than x smaller than C plus delta, f prime of x is smaller than equal to 0. So let me use another color here. For this part of the interval, f prime is smaller than equal to 0. So the function is decreasing over that part of the neighborhood. So we see what's going on here. The function is increasing on one side of the neighborhood and decreasing on the other side of the neighborhood. So the conclusion here is that then f has a relative maximum of C. Now let me comment a little bit on the assumption. Here we try to state the assumption very carefully because we would like to assume as little as possible and still get the desired conclusion. So the elephant in the room is that here we only assume the function differentiable over open intervals from A to C and C to B. We do not mention its behavior at point C. So this test is applicable even for the case that the function f is not differentiable at C, as long as it's differentiable over open neighborhoods AC and C. We have the second part here, which states the condition for a relative minimum. Now, one more application and somewhat surprising application of the mean value theorem is to prove certain inequalities. Let me give you an example here. We want to show that the function e to the x is greater than equal to 1 plus x for all real numbers x. The proof goes as follows. Consider the function f of x equal e to the x. Then f of 0 equal to e to the 0, which equal to 1. So by mean value theorem, we have f of x minus f of 0 is equal to f prime of c for some c between 0 and x times x minus 0. So the left hand side is e to the x minus 1, and the other side is x times e to the c. The derivative of the exponential function is equal to itself. So we have this equation e to the x minus 1 is equal to x times e to the c. Now we consider two cases. The first case is x bigger than 0. Then the implication is that now c must be bigger than 0. Why? Let me draw a picture here. This is 0. Now x is some number bigger than 0. C is between 0 and x. So C must be somewhere inside this interval. That's why C must be bigger than 0. Then we have e to the c greater than e to 0, which equals to 1. So we have the inequality e to the x minus 1 equals x times e to the c, which is greater than or x times 1, which equals to x. So we deduce that e to the x is greater than 1 plus x, and that's what we want to prove. Now, case 2, x is smaller than 0, then in this case, c must be smaller than 0 by a similar argument, and e to the c is smaller than 1. Then e to the x minus 1 equal to x times e to the c. So how does this expression compare with x times 1? E to the c bigger than 1, but x is a negative number here. That's why here we still have the design equality. X times e to the c is smaller, is bigger than x times 1. So finally, e to the x is bigger than 1 plus x for all x inside the set of all real numbers.